Hello, welcome to this project showcase on cloud segmentation, use both unsupervised and deep learning methods. We use Sentinel-2 satellite imagery. In this video, I will talk you through the workflow, key steps in code, evaluation metrics, and comparative results for different methods. We begin by exploring our dataset. The data consists of Sentinel-2 image chips, which spans BO2, BO3, BO4, and BO8. For each chip, we also have cloud mask labels provided. Here's an example chip RxCN captured over Ghana. After data is fetched, we start by inspecting the red band BO2 as seen in the false color representation. Areas with higher reflectance, possibly due to clouds of bright surfaces, appear in green. In this section, I use the Sentinel-2 BO2 band image as input and applied Gaussian mixed modeling with two components to perform unsupervised classification of clouds and non-cloud pixels. The predicted binary mask was compared against a manually labeled reference image. The classification achieved an accuracy of 89% with a precision of 0.93 for both classes. The confusion matrix showed around 185,000 true negatives, 58,000 true positives, 13,000 false negatives, and 4,700 false negatives. Additionally, the IOU score was calculated to qualify the overlap between the predicted cloud areas and the true cloud areas, with a result of 0.7638. indicating a high degree of overlap between the two masks. Next, we use the BO4, BO3, and BO2 bands to create a true color image. I also use GMM to perform segmentation on multiple images separately, and let them merge the result to obtain the final detection output. Here's the result. Our chip rendered as it would like to the human eye know the white cloud patches scattered across the landscape. I also perform the segmentation on the images in the ADWP folder, and here is the result. And I also use the k-means clustering method. The IOU in this case was only 0.2703, while both GMM and k-means are unsupervised clustering methods. GMM produced sustainably the results, while k-means struggled to distinguish cloud regions, likely due to this linear separation boundaries and equal variance assumption. These limitations make it less suitable for this task. And the next section of the project focuses on CNN. Because the Google Drive cannot accommodate all the content, I uploaded the zip file to the Google Drive and unzip it in the column. Here I load the metadata from a CSV file, which contains details like chip ID, location, date, and the path to the image data for each chip. While analyzing the metadata, we find there are 11,748 unique chip IDs collected from 81 locations across 91 different time steps. The bar chart highlights the 25 locations contributing the most image chips. This distribution analysis is crucial for identifying potential location biases and ensuring a balanced dataset for training robust cloud detection models. And here are also data time and location of different chips. then I still use the RxCM part. The BO4 band image is read and visualized using raster-rail, showing the image spans from approximate longitude -1.76 to -1.72 and latitude 6.94 to 6.99. A function then combines BO4, BO3, and BO2 bands to generate and display a true color image of the chip, providing a natural visual interpretation of the satellite data over this region. And next, I present several randomly selected imagery chips along their corresponding ground truth cloud masks. Each pair displays the true color satellite image on the left and its binary cloud mask on the right, where yellow represents cloud cover regions. These examples such as chip MQCQ from Macapa and chip HSWM from South America, Brazil, roughly derive atmospheric and land surface conditions. By visually comparing the images and their labels, I assess the feasibility of the cloud detection. And in the next step, we initialize the cloud model, our deep learning model designed for cloud segmentation. The model is configured to use the selected bands BO2, BO3, BO4, and BO8, along with the training and validation dataset. We also define key training components, a checkpoint callback that monitors the IOU epoch metrics, ensuring the best performing model is saved automatically, and an early stopping callback to halt training when improvements level up. This helps avoid overfitting and saves computational resources. Next, the trainer for PyTorch Lightning is set up. It is configured to use a single GPU to acceleration, which significantly boosts training efficiency. Finally, once the trainer is instantiated with all necessary callbacks, we're ready to begin model training. And next, I start to feed the model. Throughout the training, we track the IOU. The training loop continues, and each step provides insights into the model's performance until IOU epoch was not in top 1. The log highlights improvements over epochs, and by epoch 8 it improved further to around 0.86588. And then we can copy the path of it to use it in the next step. And next, I load the trend model from Safe Checkpoint. I use the dataset of RxCN and run it through the model to generate a prediction mask. I also calculate the intersection over the union, which in this case is about 0.84, showing strong agreement between prediction and ground truth. I generate a confusion matrix to examine the model's pixel level performance in more detail. This wraps up the validation phase, confirming that the CNN model performs well on unseen data. In conclusion, unsupervised algorithms, GMM and K-means were applied for cloud segmentation. The experimental results show that the GMM outperforms K-means in point cloud segmentation. I developed a cloud segmentation model based on deep learning, using LinkNet as the main architecture with MobileNet v2 as an encoder. Results on the validation set showing that the model achieves an IOU of 0.84 compared to unsupervised approaches. This deep neural network-based methods demonstrates a clear performance advantage.